Okay, it's recording. And then that's back up. Our guests, our remote students. Okay, it's 8:20, so I'm going ahead and get started. Good morning. We're starting week 4, believe it or not. Okay. Just so you're aware, next Wednesday, not this Wednesday, next Wednesday is what they call a bishop break day. There are no classes. Next Wednesday. That gives something for you to hang your hat on if you're feeling a little overwhelmed. You'll get a break day. Okay, so I posted the quiz scores on Blackboard this morning. So you can check those out of a possible 15 points, because that's what the quiz points will be, 15. And you will see where I've made comments to give you guidance, okay, and what your score is. What I recommend you do is cross-check your work on the quiz with my solution for the quiz, which is also on Blackboard, okay, in the quizzes folder. And you can see exactly how I solved it. And that might be very helpful for a number of reasons. One, if you missed any points, you got to take a little bit of time and try to figure out, okay, what was wrong with what I did? That's how we learn. And two, it shows you the level of detail that you need to provide in your work for me. Right? It should be comparable to the level of detail that I provide. Okay. And my feeling is that since you have 2 hours to do what is really a 20 to 30-minute quiz, you shouldn't have to feel rushed. And so you should be able to show me your work. Okay. So use my quiz solution as a guide. Okay. Yes.
How do we access the actual, not the solution, but the score?
It's in the grade book, right? Maybe there's a lag. I posted them this morning.
Professor, I don't have my quiz 2 solutions.
The grade. Well, I did post them. So maybe there's a lag time between when I post and when Blackboard shares them, although I don't know why there would be. Okay. But I'll check again after class to see what it's doing. Okay.
Okay.
But that's going to be my pattern. I'm going to post those pretty much on Monday morning. Okay. So we'll see what Blackboard is doing. Figure out what it's up to. That's out of our control what it does, but we have to live with it. So we'll see. So you can check, but my solution should be there too. That's in the folder that says quizzes. Is that there? Okay, at least that's there.
Yeah, it is.
Okay, good. Please don't forget, you have to, at the top of your quiz paper, write your name and then give your signature, like you were signing a check or a contract. And again, that's so that you acknowledge to me that you have followed the rules for the quiz. I'm a little bit flexible one more time on this one if you didn't do that, but I'm not going to do that anymore. You have to sign it, okay? And it has to be clear that it's a signature.
Is our answer for like a 10th difference because we rounded at a midpoint? So like you stick to a certain midpoint?
Mm-hmm.
Okay.
That should be okay. Okay. And please also make sure what you upload for your work is a PDF, not a JPEG or an image file, but a PDF, because it's only a PDF that I can then go into Blackboard and comment on. Okay?
Are you comfortable with us for your quizzes? So historically what I've done is I've just annotated the PDF that you provided using my own. Will there be quizzes or assessments where we'll need to like create our own paper so we'll have additional space?
Not necessarily. You see on this one, I actually left you some space. So I'm fine with you showing your work. In the old days, that would have been paper, and that's exactly where you would have put your work, on the quiz paper. So you can do it either way. You can annotate the quiz or exam paper itself in the spaces provided, or you can work on blank paper, but blank of course means it can have lines, but no other writing, okay? As you're thinking ahead, it's Monday, so tonight is another problem set night. Tutor is available this evening. Okay? And the next set will be due Thursday night. We've got a pattern here, right? Okay. Don't forget in lab this week, we're starting a new experiment. It's a 2-week experiment, so you won't turn in a lab report this week. You'll be getting your graded lab reports usually the morning of your lab day. So the Monday group, I posted those this morning. They may not be on Blackboard yet. Okay, so I don't know what happened with our quizzes. I'll find out. Tuesday's lab, you'll see yours tomorrow morning. Okay. In the old days, you got the graded lab reports back at the beginning of the next lab. Okay. And yes, good point. You have a pre-lab, right? There's a series of little calculations and a graph you need to make, and it's all described. It starts at the beginning of experiment 3, and it tells you what to do, okay? So you need to have that done. It says do it as a Word document. You can also do it as a PDF, but you just email it to me no later than the beginning of lab, your lab time, okay? So please don't forget to do that, because that's 10% of your lab grade for that experiment. Okay. So what I wish to do is do a little bit more practicing with projectile motion today, and then start what's called uniform circular motion, which is also a very important motion for us in physics. But I want to start with this set of practice questions, which on first glance is probably going to seem straightforward, but I know from experience, it actually gets at common misconception in projectile motion problems, okay? And it has to do with how you figure out the initial velocity of something if it was on something that was itself moving relative to the ground. So here's the situation. We have a helicopter. It's flying horizontally at a constant speed of 20 meters per second over level ground at height h. It releases a bundle of food supplies. That bundle of food supplies is the projectile that is going to undergo projectile motion. We're told to not worry about the effects of air on the bundle. Even if it didn't say that, we would assume it in this class. Okay? Then come a series of questions. But before we even answer any of the questions, I want to, this is where I hope to get at the misconception, I want to draw a sketch of at least the initial situation. What do I mean by initial? When the projectile motion begins. When does the projectile motion begin? At the instant that bundle is released relative to the helicopter. Okay? So here's my picture. We'll take the y-axis to be vertical. We'll take the x-axis to be horizontal over the level ground. Where they cross, of course, is the origin. Just so that we have something specific in mind, because the problem doesn't constrain us, let's say at the initial situation, this little box here represents the helicopter. And there it is, and it's traveling to the right, horizontally, at a constant velocity, v sub h, h for helicopter. All right? That's that helicopter. This is when the projectile motion begins. Now, what it does at this moment is it releases, or somebody releases, or some mechanism releases, this bundle of food supplies. So there it is. It's basically just been released by the helicopter, height h above the ground. Everybody understand? I've decided to draw a sketch to help me visualize in better detail what's going on. Okay, here comes the misconception part, the subtle question that trips people up. What does the word release mean? There's no velocity. Release means no velocity. But what is that? There's a little assumption built into that. What's doing the releasing? Helicopter, whoever's on it or whatever, right? So this means no velocity relative to the helicopter. Yes? A person's on the helicopter holding the bundle and they just let go. Can you visualize this? Release then means no velocity relative to the helicopter. But the thing you have to understand with projectile motion problems that your book and all the physics books are tacitly assuming and not always telling you is that the assumption is that the observer watching all this is on the ground. Okay? Not on the helicopter, on the ground. Okay? So from that observer's perspective, this is us, from our perspective, what is the initial velocity of the bundle for this projectile motion? It's the same as the helicopter. If you have no velocity relative to the helicopter, and the helicopter has a velocity relative to the ground, then your object has the same velocity as the helicopter relative to the ground. So let's sketch the initial velocity vector for the bundle. It's perfectly horizontal and is exactly equal to the v of the helicopter. Does that make sense? Exactly the same as the v of the helicopter. Magnitude of the v initial for the bundle is equal to the magnitude of the velocity of the helicopter, which is 20 meters per second. I can also tell you x initial and y initial for the bundle. Yes? What's x initial for the bundle? 0, right? Because I chose the picture, so it was at x equals 0, right? And y initial would be h. Then maybe I might ask you to sketch the trajectory, the path of the bundle. You should be able to do that on the picture, right? What's the mathematical shape for projectile motion? Parabola, right? And this would be a parabola that is at a maximum here and then just curves downward. And somewhere here will land on the ground. Yes? All right, here come the questions. A, what is the bundle's initial vertical component of velocity? What is v initial y component? 0, right? Because the bundle is given the same initial velocity as the helicopter, and the helicopter is not moving vertically at all. B, what is the bundle's initial horizontal component of velocity? That'd be v initial x. (20 meters per second). The same as the speed, the horizontal speed of the helicopter. Okay? So this is how the bundle starts its projectile motion. No initial y velocity, 20 meters per second for an initial x velocity. Its initial x value is 0. Its initial y value is whatever that height h is. Okay? C. What is the bundle's initial vertical component of acceleration? What's the initial vertical component of acceleration?
G.
No. I think Salim has an answer. Salim? Say again,
G.
Salim, please.
Gravitational
G?
acceleration.
Yeah, okay.
Yeah.
A sub y. Do I just write G like that? Negative
Minus
G.
G.
Yes? Very good. Negative G. Okay? Projectile motion, right? Gravity. Gravity is the influence. Gravity produces a downward acceleration. D, what is the bundle's initial horizontal component of acceleration? So now it's asking, what's A sub x?
Zero.
Yes. And Love, what do you think? 0. I've had multiple people now telling me 0 because horizontal, there is no acceleration, right? The only influence is gravity. Does gravity pull sideways this way? Not in my experience. Okay. So a sub x, the horizontal component of the acceleration, is 0. Here's another one. These are all conceptual, right? You don't need lines of algebra here. Just got to draw yourself a nice picture so that you understand what's going on. E, what is the horizontal component of velocity, again, for the bundle, just before hitting the ground? What do you think? Remember, the x velocity is constant. And so the final x velocity is whatever the initial x velocity was. So v final x equals v initial x, 20 meters per second. This is conceptual. You see, you don't need a lot of math here. You just have to understand physics, the physics of projectile motion. The last one I'm going to let you think about. I'm not going to answer it. You think about it for yourself. It goes like this. Suppose this helicopter speed was cut in half, still going horizontally, but now it's not 20 meters per second, but 10 meters per second, all right? And redo the whole thing. Release the bundle, let it do its projectile motion, so forth. The question is, would the fall time, the time from release till it hits the ground, would that be longer, shorter, or the same? Just going to let you think about that, all right? Because I want to go on now to something else. Remember that video I showed you at the end of class on Friday? Let me remind you of it. It had a cart on wheels that ran on grooves on a horizontal track. And it ran with very little friction in its axles. And we gave it an initial horizontal velocity. This cart was just rolling along this track. And it had a little ball, like a ping pong ball, down inside it. Turns out it's spring-loaded inside there. And when it passed that little post, the ping pong ball was fired upward by the cart, given an initial velocity component upward. Remember my question was, because then the ball will do projectile motion, up and then down. Where will it land relative to the rolling cart? Behind it, in front of it, or with it? You remember what you saw? It was the very last thing, and we did it quickly. What's that? It landed with it. Did you think about that a little bit maybe over the weekend? Could you explain to somebody why the ball lands with the cart? Not behind it, not in front of it. There's the cart. It's moving along. It fires this ball. The ball undergoes projectile motion. And it lands right back in the cart again, doesn't it? You see why is that, as it happens that way? Anybody have a thought they just want to share? Yeah.
Because the ball had same horizontal velocity as the cart, so right when you released it,
Okay, so it has the same horizontal velocity as the cart, right? You want to add something? Gravity is the only influence, and that's vertical. And remember, the vertical and the horizontal motions are independent of each other. Yes?
If two things start at the same point and they have the same horizontal velocity, they're going to end at the same horizontal velocity.
Right? They start at the same point. They have the same horizontal velocity, so they're always going to be horizontally lined up with each other, yes? Not vertically because of gravity, but horizontally, always lined up, right? That's why that lands together. Oh, pretty neat. Now I want to show you another video. This link is probably not going to open. I'll try it. Yeah, it's going to say that, and then it's not going to open. So bear with me just a second. I will need to go out of PowerPoint and okay. Now let me tell you what I'm going to do, or what we're going to do in this demo. Same cart, same track, little ping pong ball down in there. Going to let go of it. It's going to travel this way. There's a little post. When it passes that, it shoots the ball straight up. Just like before. Except this time, you may not be able to see it very well. There's a string tied between this cart going horizontally over this pulley, and there's a mass right there that's going to descend. Okay? Again, though, the cart's going to fire the ball up. Now, where do you think the ball is going to land relative to the cart? Mhm. It is. The string is attached to the cart. Behind the cart. So, but not with it anymore. Why? What's different this time? There's going to be a horizontal acceleration to the cart. Yes? That falling mass is going to cause that horizontal cart to go faster and faster. Can you imagine that? Can you envision that? But the ball is just given an initial velocity, and the string is not going to pull on that ball once it's up in the air. Okay, so let's see if that's what happens. It's going to be in slow motion again. It lands behind, right? Because this thing was accelerating horizontally, but the ball was not, okay? And I'll still let you think about the other one I mentioned in class, at the end of class on Friday. What if you did the first video, not the second one, the first one, with one end of the track tilted so that it was on an incline? Where do you think the ball would land? But I'm going to move on, okay? Let me get the board cleared. I want to do a Wiley Plus problem that involves projectile motion so that you can see the level at which the homework's going to be. We've talked about all the conceptual aspects to try to get the physics really solid, okay? That's why we do the conceptual questions, but we still got to be able to solve Wiley Plus problems using these ideas. So here's a problem. It's real-world application of projectile motion. There's an archer fish which shoots down insects off of low-hanging twigs near water by spitting water at them. Okay? And so the archer fish just squirts a little drop of water to knock the insect. So this is, you have to imagine that dot's an insect on a twig near the water surface, and the fish can see it. Okay? All right. Now the insect is located along a straight line path. That's the dashed line. That's the line of sight for the fish. Yes. At an angle phi above the horizontal, the picture shows you what they mean for the phi. And then this distance d. That's the line of sight from the fish to the insect. Of course, the fish is hungry and wants to eat the insect. So it needs to knock it off the twig. It's going to use the drop of water to do it. All right. So it's going to launch a drop of water at an angle that we're going to call theta initial. The claim is that the firing angle for the drop of water is not phi. Because the drop of water, once fired, is going to be a projectile. It's going to follow a parabola, a curved track, right? It's not going to go in a straight line once the fish fires the water. So the fish has to take this into account. The fish has to take physics 110 to figure out how to calculate exactly at what angle theta initial to fire the water drop to hit the insect. Now, to make the problem well defined, they're going to tell us some things. They're going to tell us this angle phi is 36 degrees. This straight line distance d is 0.9 meters. We want the firing angle of the water, theta initial, 4. And we're just going to add one other little restriction that the fish wouldn't have to have, but it makes the problem solvable. We want the drop of the water to be at the top of its parabolic path when it hits the insect. Okay? What's the firing angle? Theta initial. Okay, I'm going to have to raise the screen. I'll talk us through if we need to remember any of the numbers, but I need the space. So I'll have to mute the image. Okay? And so now we're doing and which one are we up to? We're up to example 2. Okay. All right. Well, the picture that was given, I think, was helpful, but I'm going to add more to it. There's the surface of the water, and the fish is right underneath the surface. Okay. And let's take the origin to be where the water drop begins its motion. All right. Now, let's remember, we go out a distance d at angle phi to get to the insect. And we know d, and we know phi. Phi is 36 degrees. D is 0.9 meters. Double check. Okay. Now let's draw the trajectory of the water drop that the fish is going to create. It's going to start right here. Okay, and it's going to have to be fired at some firing angle, theta initial. The water is. Its initial velocity is at an angle theta initial. It's not going to be the angle phi. You understand that? That's not going to make the water hit the insect. What can you tell me about theta initial relative to phi? If it's not equal, it's either bigger or smaller than phi. Thoughts? I think it's going to have to be bigger because the water drop is immediately going to start following a parabolic trajectory. And we have to get to that point and be at the high point of the parabolic path, right? High point. So it's got to do something roughly like that, yes? That's the actual projectile motion path of the drop of water. And so the water has an initial velocity down here at the firing point that's tangent to that trajectory, v initial. And the angle of v initial with the horizontal is what we call theta initial, the firing angle. You understand that? Our job is to find that firing angle, theta initial. Everybody understand that? All right, now let's write down some things about that initial velocity. It has 2 components, an x component and a y component, yes? That initial velocity. It's got a horizontal component and a vertical component. We need to be able to write down an expression, not numbers. Right? I don't have any numbers to put in, but I can write an expression with symbols. The x velocity component would be right along here, which would be adjacent to the angle theta initial. So you would have length of hypotenuse, magnitude v initial, times cosine theta initial. You see how I got that? Your book talks about that, and I do too, in the lecture on projectile motion. I'm going to shorthand that and write it like this. V0 cosine theta 0, where the V0 with no other symbol means the magnitude. You see what you would write for V initial y component right here, the vertical component? What would be the expression you would write?
I know that the initial without the vector is, like you said, is a magnitude of p, right? But does it work with any other variables?
Well, it works for any vector. Doesn't have to be a velocity.
Any vector?
Yes,
So you just
any
don't
vector.
write a vector, it's the magnitude.
That's right. That's right. So what would you write for this one? V initial sine theta initial, theta 0. Okay? Now, it may seem a little hopeless. I don't know anything about that V initial, do I? I don't know the magnitude of it, right? I don't know how fast the water's going when it leaves the fish's mouth. Nor do I know the angle theta initial that the fish spits it at. It's the theta initial I have to find. One's first thought might be, how can I find the theta initial if I don't even know the V initial magnitude? Well, we have to have what your author of your book would call a little bit of physics courage and systematically set it up and apply the correct physics concepts, then do the math and try to solve for the thing they ask for. And presumably we will discover that when we solve for the thing they ask for, any symbols that we introduced for things that weren't given cancel out in the algebra. And you get a final symbolic answer that is only in terms of things that you were given. That's how pretty much all the Wiley Plus problems are going to go. So let's keep proceeding. So I need some more physics ideas that I've got to come up with on my own. And here's the important one. This has got to be on the blue dash curve. It's got to be the high point of the parabola. We're told that. Tell me something that you know about projectile motion when you're at the high point. Malachi. Which velocity? Well, there's something to do with the velocity that's zero, but we've got to be very specific. Be at the top point, but what, anybody know what I'm talking about? Adrian? It's only the y component of the velocity that is zero. Is the x component of the velocity zero? No, the x velocity is constant, so it can't be zero. So at the high point, you know what? Let's call that h. Why not? I can introduce symbols, I just can't have those symbols in my final answer. So at y equals h, v sub y equals 0. Yes? You have to figure that out for yourself from the problem. It doesn't going to tell you that. And that thought process is called thinking like a physicist. All right, let's use that to get an expression that's helpful. Thoughts on an equation to use now to take advantage of this information? Yes. Well, yes, if you're talking about V? H. Oh, well, you want to use Pythagoras. We can do that. I'll label this other side here L, and we are going to come to that, using that. But I want to use this specifically. I think Hannah has an idea. Okay. You're telling me a constant acceleration equation, aren't you? I think that's what you are telling me. Yeah. Is that okay? Is it okay to go to the constant acceleration equations with this problem? Sure. Right? Projectile motion is a constant acceleration. A sub y equals negative g, constant. A sub x equals 0, constant. You have to be able to figure out for yourself that I get to use all the constant acceleration equations, and I got to figure out which one is the best one to use. All right? I think you were saying the v squared one, but for y components. So vy squared is v initial y squared plus 2ay times delta y. All those subscripts must be written. Now let's plug in things that we know. Let's apply it to this high point. At y equals h, vy equals 0, right? We just said that. So for the vy here, it's 0, right? 0 squared is still 0. But the 0's here, right? On the left, equals v initial y squared plus 2 times a sub y. A sub y is negative g. And what is delta y? Between here and here. H, right? H, right? Now we just rearrange. I'm going to write down an expression for h. I'm solving this for h. Not because I can get a number. I can't get you a number for h yet. But it's going to be helpful. Now you can do the algebra. You get h equals v initial y squared divided by 2g. with no negative signs anywhere. That's going to shut down. That's okay. Now for the v initial y squared, we can go ahead and put this expression in. It turns out it will be helpful. The initial y is v initial sine theta initial, and it's here and it's squared. So v initial squared sine squared theta initial all over 2g. You see what I did? Notice it's all symbols. I don't care if I don't know numbers yet, but I know I'm writing down correct physics. Okay? All right, I've learned something about this side h. And we've had a kind of a suggestion, I think, that the way we're going to end up getting phi is by looking at that right triangle that phi is part of. And I've got one leg h, and I've got an expression for h, even though I can't get you a number. So let's look now at the other leg, L. All right, let's see what we can say about L. What can we say about L? Now this part, well, there's more than one way you can get a formula for L, but that's what I want. I want a formula for L that kind of goes with this one for H. More than one way. Thoughts? You have a thought? D times. Oh yeah, you're right. L is equal to d cosine phi. Absolutely. But what I need though to use is the physics of projectile motion to get an equation for L, like I did for the H. And then I'll come to what you're saying. Okay? Do you have a, I don't know if you had your hand raised. No? Yes.
We use the constant acceleration equations, but in the x direction.
Okay. You can do that. And you absolutely can do that, but it will involve time. And you'll have to find the time to go from there to there. Again, not a number, an expression. You can do it. It's a little bit messy. So I'm going to show you a shortcut, but that method is not wrong. The shortcut is to note that if we fired from ground level, it would come back down to ground level eventually. We've gone halfway across when we're at the high point. I mentioned this equation called the range equation, which gives you the horizontal distance traveled from firing to landing if the firing and landing are the same height. So is not L exactly half of this range? All right? So it's, and the symbol for range is big R. It's half the range. And then you just look up that formula for the range and divide it by 2. Okay? So I'm going to write down what that is. It's V initial squared sine of, watch out, look what's in the argument of the sine, 2 times theta initial over G. That's the formula for R. But I have 1/2 of that, so I have a 2 in the denominator. Okay? Now remember, when you take quizzes and tests, you will have Wiley Plus at your disposal. So you got to at least be familiar enough with the content to say, wait a minute, Wiley Plus derived a formula for this range. All I need is half that. Okay? So if I call this equation 1, the one for H, and this one equation 2, the one for L, I contend we're almost done. Okay? We have almost everything we need to get, what do we want to get? Theta initial. All right, so a couple of you have been telling me to focus on the right triangle drawn in black with hypotenuse D, leg H, leg L, angle phi, because that is a right triangle, right? And let's just use some trig that we know. How about tan phi? You have to remember, tangent is opposite over adjacent. So for phi, the opposite side is length h, and the adjacent side is length L. Yes, tan phi is h over L. Now, substitute these equations. Substitute equation 1 for h, and substitute equation 2 for L. let's do that and see what we get. Tan phi equals h. Make sure you do these right. You got to do your algebra carefully. V initial squared sine squared theta initial over 2g. That's just the h. And then that's got to be divided by L. And L is that, which is itself a fraction. But when you divide by a fraction, it's like multiplying by its inverse. So I'm going to multiply by the inverse of L. 2g over V initial squared sine of 2 theta initial. You got to do this algebra with extreme care. You got exponents that are 2 here, an exponent, but you got a 2 inside the sign here. You have to have full concentration. But now do you see that this is going to simplify a lot? 2 downstairs, 2 upstairs, cancel. G downstairs, G upstairs, cancel. V initial squared down upstairs, V initial squared downstairs, cancel. Wow. Let the dust settle. What's left? Hopefully something. Tan phi equals sine squared theta initial over sine of 2 theta initial. Still have to have my physics courage, because that's got to be simplified. Thought? Yeah, there's a trig identity for sine 2 theta. Dust that off. It's handy. Okay? The trig identity, that's going to go in the denominator, for sine 2 theta is 2 times, I should say sine 2 theta initial, 2 times the sine of theta initial times the cosine of theta initial. That's called the double angle formula for sine. A good physicist or engineer will just have that in their head. That's how commonly you use it. Now do you see what happens? More cancellation. Got one factor of sine in the denominator. You can take one factor of sine in the numerator, but just one. Now what's left? Sine theta over 2 times cosine theta. But what's sine theta over cosine theta? So this is tangent theta initial over 2. But I don't want phi. I want theta initial, right? Okay, multiply both sides by 2. Tan theta initial is 2 times tan phi. So theta initial is the inverse tangent of 2 times the tangent of phi. Wow, the only thing I needed to know was phi. You notice that it gave me d? Do you remember that? Do you remember it gave me the distance d? Do you remember the wording of the problem? It told me not only what phi was, but it told me what d was. It didn't tell me anything else, did it? Nothing else. The d and the phi. At first glance, you're thinking, I don't have enough information with d and phi to answer this problem. Actually, our symbolic answer tells us, I don't even need to know d. Right? The only thing you have to tell me is the line of sight angle from the fish's eye to the insect, the phi. That's the only thing I need to know. See the power of a symbolic answer? The algebra often simplifies a lot, more than you might ever guess. And you get an answer where you know exactly what symbols you need to be given. So the phi, remember, was 36 degrees. So you take the tangent of 36 degrees, make sure your calculator's in degree mode, multiply that by 2, and then take the inverse tangent. You will get 55.5 degrees, which is indeed bigger than phi, right? Because we said it had to be. So the fish has to fire at 55.5 degrees. Of course, the fish learns that just by trial and error. The fish does not take Physics 110. Okay. That's a Wiley Plus problem. That's projectile motion. I hope you understand that. unlike perhaps in high school physics, it's not just going to be plug and chug into equations. You're going to have to do a lot of thinking. What physics ideas do I need to bring to bear? I might have to do quite a bit of algebra before I ever plug in numbers. And then you're learning to think like a physicist. Okay, now let me, if I may, spend 5 minutes talking about, let's see here. Yeah, let me get out of here. Talking about circular motion. We'll start today and we'll continue on Wednesday. I gotta power this up. This thing. We don't have many learning objectives. Okay? We're talking about what is called uniform circular motion. We need to be able to sketch the path that a particle takes in uniform circular motion and basically tell me everything there is to say about the velocity and the acceleration vectors during that motion. We need to apply the relationships between the radius of the path, the period, and the particle's speed, and the particle's acceleration magnitude. So let's start thinking. First, let's get the brain firing on this new idea. Hopefully the words circular motion are clear to everybody. The particle is moving in a path that we would call a circle. And my video lecture reminded you of the things that you learned about circles in high school math that you still need to know, okay? Like the formula for a circle, how it's related to the coordinates of the center of the circle and the radius. All right, and then we need to be able to draw the velocity vector on the circular trajectory and the acceleration vector. But let's be clear first about what that word uniform means. Who remembers from the reading or the video lecture? When we say uniform circular motion, that uniform implies something special. What's special? The particle is moving in a circle with its speed constant. And speed is magnitude of what vector? Velocity. So the particle is moving in a circle with the magnitude of its velocity constant. Tell me what's wrong with this statement. Student says, oh, we studied circular motion today with constant velocity. What's wrong? There's something wrong there. Yes.
Velocity is some direction and magnitude, so that implies that it's staying the same direction.
Correct. Constant velocity can mean only one thing, moving in a straight line at constant speed. I don't think that's a circle, is it? It is impossible to move in a circle at constant velocity. Absolutely meaningless. Okay? So be careful of that. What are we saying is constant? The speed of the motion. What's the closest analog I can come to in your daily life? You heard about the traffic roundabouts that a lot of cities have? Assume that the traffic roundabout is a circle. You get yourself in, don't do this, by the way, in real life. You get yourself in one of those and set the cruise control on your car. And just keep going in a circle. Then you're going in a circle at constant speed. Don't do that in reality, okay? It's not safe. But that's an example of what I'm talking about. Okay, here's another thing that people often say. Oh, well, given what we know about the velocity in uniform circular motion, the acceleration of the particle must be 0. What's wrong with that? Acceleration is not constant. So it can't be 0 because it has to be changing. Okay, why isn't the acceleration 0? I thought the speed was constant, and I thought acceleration was derivative of speed. Okay, that's right. Acceleration is a vector with a magnitude and a direction. It could be possible that its magnitude is constant, but its direction isn't. What's wrong with the statement, acceleration is the derivative of speed? So what is acceleration the derivative of? Velocity. Are speed and velocity the same thing? No. Didn't we just say the velocity is always changing? So there must be an acceleration for uniform circular motion. Who knows which way the acceleration points? What's its direction? Towards the center of the circle. Which means as the particle goes around, it's always changing direction. Yes? Yes, it's always pointing towards the center, but that means its x and y components are changing all the time so that it can point towards the center. Yes?
Mathematically, is that because it's tangent to the tangent line? So it ends up being the secant line?
It's because the velocity vector is changing in direction only, not magnitude. The only part of the velocity vector is changing is direction, not magnitude. So the vector for the rate of change of the velocity turns out must be exactly perpendicular to change just the direction part. Okay? Who remembers the formula for the magnitude of this fancy acceleration for a particle moving in a circle? Colin?
Oh, it's the velocity squared over the radius.
Yes. The magnitude of the velocity squared divided by the radius. V squared over, we call the radius, R. Okay? All right, so what we're going to do on Wednesday is we're going to start some practicing with these ideas. Okay? Okay.
Can I ask a question about the range formula?
Yeah.
So in the range formula, I wrote down this because I was in the video. Is that the magnitude of?
Range is just a distance, so it's got to be a positive quantity. Range is not a vector. It's just the distance.
But this part right here, v sub 0 squared, is that the magnitude of velocity?
It's the magnitude of the initial velocity squared.
Okay.
Yep.
Got it.
Okay.
Really?